Oh, the futility of humanity. Is she moving? Does she have velocity? Ask her, she'll say yes, I've got velocity up. Ask that man, she might say, you bet, she's really moving fast. Is the escalator moving? Does it have velocity? Oh, poor woman, keep moving. For your velocity might be in positive and the escalator might be in negative, but if you keep fighting, you might find you do have some velocity left over when the vectors are added. Keep going. Don't give up, lady. And that's tonight's topic. Relative velocity. There you go. There's really nothing new in this topic tonight. We're going to just look at situations in which the coordinate system is moving. In other words, you're a lady on an escalator, or you're on a bus that's moving. Or perhaps you're a boat, but you're on water that's moving. And we'll be solving some relative velocity problems. On the book in 6.3, we see this supposedly explanatory thing, which is that the velocity of any object A to B added to the velocity of any object B compared to C will give you the final velocity of A compared to C. Sounds complicated, but actually it's a very simple idea we've done before. I'm going to just take this example from the book. Suppose we have a bus that's going 8 meters per second down the street. I'll establish that as my positive. And you're on this bus walking forward. So you're in the same, moving in the same direction as the bus. So that'd also be plus 1. In this case, you would be the VA to B. That means your plus 1 is your velocity compared to the bus. We'll make you A and the bus B. The bus relative to the street is plus 8 meters per second. So we'll make that the B to C. So if you want to find your velocity, remember your object A, compared to the street, C, it's just simple vector addition. You should be experiencing a little deja vu right about now. We could reverse the situation and have you moving to the back of the bus at 1 meter per second. Now we'll still keep the bus going plus 8 meters per second, but your velocity now I'd have to put as negative because of the direction issue. But it's still just adding it up, and that's how you do it. It's going to be that simple. Let's look at an example though where it's not aligned, when they're actually two, not just different directions, but two different dimensions. There's a problem 3 right out of your textbook about people on a boat going 4 meters per second relative to the water, and they roll a marble but perpendicular. Well, the boat's going east, they roll the marble north. So how do we handle that? The good news, there's nothing new for a problem like this. It's stuff we've done before. When you're going to add vectors, but they're not in the same dimension, if you're fortunate enough to have them at right angles, then you can do this. It's just going to make a right triangle. Good old Pythagoras. We'd have our vector of the boat, the longer one. The much shorter one there heading north should actually be moved tail to tip. That's how we get the resultant vector. And we can just use the Pythagorean theorem to figure out exactly what would be the length or magnitude of the resultant velocity vector. This one would be 4.1 meters per second. This is right out of your book. I'm just reminding you and showing you how easy this is. Also reminding you for every vector you need to get a direction. Now the way to handle it in this situation would be through the tangent function. The tangent of the opposite, which is the marble's vector velocity going north, divided by adjacent, which is the boat. And when you're done with these, check your units are correct. Check that your signs make sense and the magnitudes are realistic. So let's take it some problems in the book. We're going to only do 2 of these tonight, and number 24 is going to be your homework. So in 22, you're riding on a bus moving slowly through heavy traffic at 2 meters per second. You hurry to the front of the bus at 4 meters per second. So you relative to the bus, you actually have the greater velocity vector, 4 meters per second, and that's the bus. If I want to, in this case, find out you relative to the street, I just need to add those two velocity vectors together. So if someone was on the street watching you run, they wouldn't say you're going 4 meters per second or 2 meters per second. If they were describing your motion, they would say you're going pretty quick, 6 meters per second. Just like someone going down the escalator might describe that woman running up the escalators going pretty fast. It's all relative velocity. Let's do one more. 23, we have Rafi pulling a toy wagon at a speed of 0.75 meters per second. There's a little caterpillar on it who's crawling backwards to the rear of the wagon at 2.0 centimeters per second. Now, do you see why I made that vector so small? 2 centimeters per second. Now we have the wagon. I'll make my object B compared to the street is plus 0.75. But if I really want to keep apples to apples and keep my dimensions aligned, I have to convert my centimeters per second to meters per second. So I can do that, as we've already seen in chapter 1. And when I'm done, I see that the caterpillar really has a magnitude of 0.02 meters per second and in the negative direction. So in this case, my A to B would be the caterpillar to the wagon, and that would be negative 0.02 meters per second. My B to C would be the wagon to the street, which would be positive 0.75 meters per second. Add them up, and my caterpillar to the street would be positive, still in the direction of the wagon, of course, but 0.73 meters per second. The caterpillar is effectively moving a little slower than the wagon if you are watching this motion on the street. And now for your assignment. This is the one you have to do on your own. You may have to pause. I want you to solve number 24. Write the solution on a piece of paper and bring it in on Monday. So write the solution on a piece of paper and bring it in on Monday. That's due Monday. And I'm not quite done yet. There's one other thing I want you to check out for homework. If you go into the physics classroom that we use for mopping and instead go to the Shockwave Studios, there's a online lab called Riverboat Simulator. And instead of waiting until you come to class and finding out you don't have Adobe Shockwave, I want you to first check this out. Now this is a very neat little simulation. It's very low tech. It's easy to use. We can change the river width, the river speed, the boat speed. We can even change the initial heading. And we're going to use this for a lab, a simulation lab that we do. I can have it show velocity vectors, or I can click here and instead have it trace the path. We have all these different options that make it much easier to visualize relative velocity. Let me start with one, for example, where I'm just going to trace the path going straight across the river. I have absolutely no velocity from the river. You'll notice that it takes about 14 seconds for that boat to cross. Now let's add I guess we could call it a y component. We're going to add river speed and start it again. And what's interesting, of course it's going in a different direction. You can see that that traced line will be greater, a greater magnitude, but notice you still cross in 14 seconds. A great little demonstration of how the horizontal component still works independent, and that these dimensions work independent. Even now, when the river is up to a raging 4.1 meters per second, he's still crossing at 14 seconds. So the horizontal component is still the same. Well, there you go. Have a good night.
Times in Babylon, that's what I'm counting on. Before the dam goes up at the